on the cloud or micro? Oh, okay, you got it. Okay, thanks. Yeah, so welcome to today's delegate assembly. So yeah, we have these every 2 weeks. So I'm going to give this week's one. It's kind of going to be focused on time domain science. So these are notebooks O7A and O7B on the Rubin Science platform. So yeah, my name is Ryan Lau. My interest, I'll have like a short bio slide that I'll give in the next one, but just also to give some more context about today. There's updates that we made to these two notebooks using the four-source UnDIA object catalog. So part of this is to demonstrate the utility of that particular catalog, the difference between that and like the DIA source and DIA object catalogs for doing different time domain science cases. Like if you're interested in discovering or identifying certain types of explosive transients in the Rubin data, and also variables, which that's O7B, and so transients is O7A. Okay, yeah, since this is the first time I'm doing this leading this delegate assembly, and I'm relatively new to this community science team, so I figured I'd give like a short bio. So yeah, I'm born and raised in Honolulu, Hawaii. Now I'm an assistant astronomer at NSF's NOR lab here in Tucson. I've been here since like last summer, so still, yeah, relatively new. Moved here in July 2022 from Japan, where I was for about 4 years. And yeah, part of my time here in Tucson is, or as an assistant astronomer, is spent as a community scientist on the Rubin community science team. I got my PhD from Cornell University in 2014, working with Terry Herter. And my thesis, or my thesis was on studying the galactic center with SOFIA, the Stratospheric Observatory for Infrared Astronomy. So this airplane with a 2.5 meter telescope, which is sadly no longer operating. But I think it's been retired and it's coming here to Tucson, I think, to be displayed in one of the museums here. And yeah, this is just a picture of me in like 10 years ago, like one of my first flights in SOFIA, where I had no idea what I was doing. And here's my my PhD supervisor. So yeah, my research interests are mainly in dust, massive and evolved stars, stellar transients and variables, and infrared and time domain astronomy. And so that's one of my main motivations of being part of Rubin and part of this community science team is I'm super interested in time domain astronomy at both like optical and infrared wavelengths, where you can really start to address some of these links between dust production and massive star evolution, which are kind of intrinsically linked. So yeah, I'm really excited about synergies between like different facilities like the like JWST, Rubin, and also other like NOR lab facilities, Gemini, Kitt Peak, CTIO. So yeah, lately I've been involved in JWST observations like this one you see here on the right. So these are observations of this massive binary star system called WR140. It's a Wolf-Rayet binary that produces these dust shells every 8 years. And so you can see these concentric dust shells from this system that's been produced for the past like 130 years. So yeah, just recent observations that we took with JWST. And hopefully we can find transients or variables like these with Rubin outside of our galaxy. So that's kind of my research interest in my bio here. And if anyone's interested in any of this, like feel free to send me an email or Slack message, and I'd be happy to talk about this. Okay, so let me segue back into the agenda for today. So not really any announcements, I think, unless Douglas or Greg or Tina, there's anything to mention, but I think we're not too much to announce. If anyone has any suggestions for breakout room discussions in the second hour of today's delegate assembly, yeah, please feel free to let me know, or you can suggest it in the chat. And then we'll keep that in mind for making breakout rooms, or just keep this in mind as we kind of go through these notebooks. You can make those suggestions and then create these breakout rooms. So I'll pause for a little bit here. Right, and then so yeah, the main I guess presentations or the main tutorials today are going to be going through O7A and O7B. So these are notebooks on the notebook aspect in the Rubin Science platform. So O7A is a little bit long, so I might skip some of the beginning parts that go through like the detailed parts about the different catalogs, about the DIA object and DIA source catalogs, and kind of just jump straight to the identifying like type 1A supernovae. And I might more focus on the new things that we've updated in these notebooks, which is kind of the inclusion of the force source on DIA object catalog to do time domain science. And so the difference between these notebooks, O7A is more focused on like transient type of science. So like for finding supernovae, and then O7B is more focused on like variables like R Lyrae stars, doing a kind of like Lomscargel analysis, making a periodogram, and using this force source NDA object catalog to do that, to kind of get the force source photometry of these different types of variables or transients. Okay, so that's all the slides I have. So now what I'll do, and if everyone wants to kind of follow along here, so we'll access those notebooks. First, we can go through to the data.lsst.cloud page. And then, if you haven't logged in since, I guess, February 23rd, lots of stuff has changed. And so that's what the past couple delegate assemblies and I think Stack clubs have been dedicated to making sure that that you're able to open and run your account easily. So I might not spend too much time if you're having some issues with this, but I think there's lots of instructions how to do it. I think there's recordings. And then we have several members of the community science team who are on this call who can probably help you out with this if this is affecting your access to the Rubin Science platform. Okay, so I guess let's see. So since I'm already logged on here, what we'll do is just go to the notebooks. And then let's see. So I have like kind of a mess here about with different files that I've loaded up. But what we'll do is we'll go to notebooks. This is where the tutorial notebooks are. And we go to tutorial notebooks here. And then here's the list of all the notebooks that are active and updated. So the two ones that we'll be working on are the ones here. So we can first start with O7A. So O7A DIA object samples. So click that and it opens up here. All right, and so sort of like all the other notebooks, there's a description here of what this is for. This has been updated, let's see, within the past couple months, I think, because this was originally made by Melissa Graham to demonstrate the DIA object table or catalog to identify type 1A supernovae. And then I've updated this to, I guess, demonstrate how we can kind of further this analysis using the force source on DIA object table here. So that's force source on DIA object. And kind of the point of this notebook, or at least the first part, is to give an introduction to the DIA object and DIA source tables. So that's the first part that I might skip over because it's a little more technical, and it's, in my opinion, I think those might be better going through on your own to get an idea of what kind of exactly the technical things you can do with this table. And I might skip to the section where it goes directly into the identifying type 1A supernovae based on certain constraints on the luminosities and the durations that you have from those explosions that you can use to identify type 1A supernovae in Rubin data. So just a reminder, this is all with the DP0.2 data set. So simulated data that will be very similar to what we have with Rubin. All right, so the other thing you can do too, so here's just a quick introduction that you can read through. These are the three catalogs or tables that we'll be using in this notebook. So DIA source, these are measurements on each visit. So each image that gets kind of difference. So the DIA in front of these stands for difference imaging analysis, I think. Whereas there's regular source and object tables that are just on the every single kind of visit or image of a particular part of the sky. So these images have been differenced with some reference image. And then the idea is you can see any types of variables or transients that that pop out of that have changed since that reference image was taken. Let's see. Oh, okay. I see. Request to make this full screen. What's the best way to make this full screen here? So I just do window, or maybe just click this.
I think if you click on the file over on the side here, hold on. Click on this right over here.
Let's see. Okay.
Right, yeah.
Oh,
Okay.
that's
Right, right.
Thank you.
Okay, cool. All right. Okay, so yeah, hopefully this looks a little bit better. Let me continue. So let's see. Yeah, so the DA source catalog identifies any kind of transient or variable or changing thing after a reference image has been subtracted to this new visit image. And then if there's a source that pops up with a signal to noise ratio higher than 5, it gets put into this DIA source catalog. Then you have this DIA object table that has a bunch of different statistics on the variability of a particular object in the sky. So it looks at the summary of DIA sources associated with the DIA object in a given kind of sky location. So yeah, the way I think about this is like a DIA object is like, I don't know if it's one variable or one transient in the sky, like that's the object. And then a DIA source are all the different observations or flux measurements of that particular thing. So a single DIA object will have like a bunch of different DIA source measurements attached to it. And then there's this force source on DIA object table, which are the results of forced source photometry. I think forced PSF photometry on every single visit image that you have of that particular object. It forces like a PSF fitting thing. And even if it's there or not, that's the result of that. So you're going to have much more measurements from this force source on DIA object table than with DIA source, because DIA source is only picking up the detections that are greater than 5 sigma on the difference image, whereas force source is where an object is, and you're running this force source PSF photometry at the location of that object on every single image that includes that object. And so these are the things that I hope to make kind of more clear in these two notebooks, 07A and 07B. Okay, so to start off here, we'll just load the package imports here. And then start the tap service. So defining these functions and parameters that we'll be using throughout the notebook. So this cosmology one here, when I saw this, I was a little intimidated by it at first because like, oh, what is this for? But this is just to convert redshifts to distance moduli. So since we're looking for type 1a supernovae in between like a certain redshift range from like 0.3 to 0.1, all this function does is it converts that into a distance modulus, so that we know how faint or how bright we expect these supernovae to be at given distances or given redshifts. So that's all this is kind of setting up here. All right, so then here's a different style kind of parameters for plotting light curves to make things look cool. And here, okay, so this is the section that goes into like a lot of detail on the DIA source and DIA object table. So yeah, feel free to look at this if you want to. It goes into really some nice detail about what's the important or some of the important parameters are in these tables. You could also go to there's a schema page here that or the schema browser page that goes through what's all the different parameters on each of these tables are. So you could just go to like the object here, and then here are all the different columns that tell you what each of these things are here. So this is another way to kind of look through this to get an idea of what the tables provide. Let's see. Oh, back to this one here. Okay. So like I mentioned, I'm going to skip through some of these. These aren't directly related to finding 1A supernovae. These are just going through the DI object catalog to show what some of these parameters do. But since we're doing 2 notebooks today and focusing more on the updates to the notebooks, I'm going to skip through these. And then I think there might have been previous delegate assemblies where this section has been gone through since 07A has been around, I think. So you might be able to find that there. But if people are really interested in going through this, maybe in a breakout session, I can, that might be a good topic to walk through if there are people who are interested in the finer details of the DI object and DI source catalogs. Okay, so if we skip down here to section 3, so now what we're going to try to do is we're going to use these the DA object table to identify transients that are potential type 1A supernovae. So this is kind of like just an example science case and how we can use these different tools on the Rubin Science platform to do science and to find things that we're interested in. The one here is focused on 1A supernovae, which is kind of nice because the light curves of these things are very well behaved and fairly well understood. So we have an idea of how bright they can be, of what their duration is, based on the detection limits that we have, that we'll have with Rubin. And so we can search for these types of things in our simulated DP0 data set, which has type 1A supernovae incorporated in the simulations here. So yeah, you can see some of the details here about 1A supernovae. Yeah, the real benefit to studying these or to demonstrate these here is that they have very homogeneous light curves with similar peak absolute brightnesses. So yeah, around -19 in B band. One of the important things to keep in mind here is that we're assuming that the Rubin data will have a limiting magnitude of around 24.5 magnitudes, so our band limit here, and that kind of sets the threshold on like kind of the faintest types of 1A supernovae that we can find, and kind of relates to the distance as well. So if we're looking for a low redshift 1A supernovae between redshift of 0.1 to 0.3, this is what we'd expect those to look like. And here's their apparent magnitudes here. So each of these have been kind of shifted based on the distance moduli that you'd expect for them to be in these particular redshifts here. So you can see the ones that are further away in like a Z of 0.3 galaxy would be fainter. And then here's one that would be closer here, like a Z of 0.1. And then, yeah, I guess Melissa has put a warning here about this, that it's, I guess, more of a back of the envelope way to try to identify these. I'm sure there are much more rigorous routines that are used to and will be used to pick out 1A supernovae. But I think this is more of just a demonstration in how you can use these, how you can use the Rubin Science platform and these tables or catalogs to identify transients that fit into certain kind of parameters that you give it, or certain constraints that you give it. All right, so here in section 3.1, we can establish light curve parameter constraints to identify these. So actually I'll scroll up a little bit so you can see this plot here. So right here, we're defining the minimum and maximum redshifts of the supernovae that we want to find. So between 0.1 and 0.3, we have the maximum, we define the maximum or the peak magnitude that we expect, peak absolute magnitude that we expect of these 1A supernovae, so about -19. And then there's a range just to give some wiggle room in case some of the supernovae tend to be half a magnitude brighter or half a magnitude fainter than that, than this specified here. So yep, execute that cell. And then in this cell here, so this is where it's using that cosmology package, and it's just grabbing the distance modulus of this specified redshift here, the minimum, and also this line here, the maximum. And then this is the peak magnitude that we have. So the combination of these two will give us the apparent magnitude for the minimum redshift distance and the maximum one here for the maximum redshift. And then minus this range that we specified here, so minus 0.5 and then plus 0.5 here. So when we execute this, we see that the apparent magnitudes will be between like 18.8 to 22.46. And I think, yeah, these are the peak magnitudes that we would expect from 1A supernovae, given this redshift range here. Right, and so we can also define the other bands. So this is just the R band one here, or the R band magnitude range that we specified here. Rather than going into detail in figuring out or putting more detailed constraints on the G and I bands, we just specify that as around 24 magnitudes. So it's kind of mentioned here, it's just to enforce that there's at least a detection in the G, R, and I filters, because it's nice to have more filters with detections so you can get the color information from these supernovae as well. Okay, so let me execute this. All right, and then you can also define the minimum and maximum amplitudes. So this is based on this plot here. So the amplitudes that you expect to detect based on the, I guess, the non-detection threshold, and then the maximum amplitude. And so based on this, the minimum amplitude that you might expect for a Z of 0.3 supernovae, it's kind of maybe between here-ish and here. So maybe 2 magnitudes or so, or maybe a little bit less. And so I think we'll be a little more generous here and call it 1.5 as the minimum magnitude. But you can see here, it's almost around 2. And then the maximum magnitude is from here to here. So it looks like maybe 5 magnitudes. And then if you add a little bit more wiggle room, so you can get ones that look a little bit brighter. So that's about 5.5. So that's where these parameters are coming from. Just the amplitudes that you expect based on these based on what you'd expect for supernovae at these different distances. So the closer ones will be brighter than the ones that are further away. Okay, so we'll execute that. And then in this next one, this is just defining the number of measurements that you want. So photometric measurements of these supernovae that you want to have. So just setting a minimum threshold to 15 and a maximum of 100. And I think the idea here is just to make sure your 1A supernova light curve is sampled well enough so you can do your analysis on it. So a maximum of 100. And I think this 100 number is coming from this duration, or it's coming from the amount of visits you expect for a supernova. And so if you have something greater than a year, there's something weird going on. So that's where this maximum value is coming from. And then a minimum of 15, since you probably want more if you want a really well sampled light curve of your supernova. Excuse that. And then here, this is just setting the duration of that outburst or that transient that you're going to search for through these catalogs. So either we'll set a minimum to 50 days and a maximum to 300 days. And again, you can kind of look at this plot here, and you can see that the minimum that you might expect, the duration of this detection here, is about 50 days. It actually looks a little bit longer, but also just to make sure we're not missing any fainter stuff, setting it to 50 days. And this large one here, or this brighter one here, looks like the duration is on the order of 300 days. So that's where those constraints are coming from. So we want to look for, basically what we're doing here in section 3.1 is setting the parameters to identify things that look like this and this as the minimum and maximum constraints on the light curves. Okay, so I'll execute that. Okay, and then here is where we're putting in some of these constraints here. So we're running this tap query to search for only 1,000 of these DIA objects that fit some of these constraints that we specified. So we're not using all of the constraints yet. We're using just some of them. We're using the number of detections as a constraint, and then we're using the peak, minimum, maximum peak brightnesses and amplitudes as a constraint here. So some of these some of the constraints discussed in the previous section haven't been applied yet. And then we'll execute this cell. Okay, that was pretty quick. It says it should take a minute, but I think, things have been quicker. And then if you want to, you can check out this table. So the results of this search have been saved as DIA objects, I guess. So we can look at that. And then, here are all the 1,000 candidates that we've identified based on just a couple of our constraints that we set in the previous section. So you can see here's the number of DIA sources associated with each DIA object. And so each candidate is associated with a certain DIA object ID, and that's what you see here. So those are like the unique identifiers that you have for each candidate or each transient candidate. And then there's like the number of DIA sources there. All right, so this one here, or this cell here, is plotting a histogram of the brightest magnitudes and light curve amplitudes. So yeah, for some reason, this looks a little funny here, and I don't exactly know why. I'm not sure if anyone else's looks like this. But yeah, I've been having some issues with that one for some reason. Yeah, I'm not sure. But this here on the left is characterized the brightest detected R-band magnitudes. And here the amplitudes on the right. Yeah, okay, so it looks like this is popping up as, I'm not sure. It looks like there's just a bunch of different, maybe the ticks are too, or the bin size is too small, where the text here is just blending all together. So that might be something we need to look at. Okay. So this is just presenting like some statistics on the data set that we're looking at, or the candidates that we've identified here. But in section 3.3, so we can now start to apply some more of our constraints that we have. So the light curve duration constraints to better identify potential 1A supernovae. So to do this, what we're going to do is we're going to use this parameter in the DIA source table, this midpoint TAI, which gives the time of the observation, I think in MJD. So this cell here, we're going to define this duration column in this DIA object table that we created up here. So right now, these are the only parameters. And this is why we haven't done the duration constraint yet, but we're adding that now. So we're defining this duration table. Right now, it'll just be blank zeros. But what we'll do is we're going to do a search through the DIA source table for all each measurement associated with a particular DIA object ID, and then reading in the timing of that observation, so the MJD of that observation. So what this cell is going to do here is it's going to go through, for example, in this, it'll read in each of these DIA objects. It'll read each of the DIA sources, so 59 DIA source measurements, and then it'll grab the timing of that observation, and then it'll use that using the maximum and minimum duration from all of those observations, and then that's what will define as the duration of that particular object or supernova candidate that we have in that table. So that's what this is doing here. It's using the object iterating on the object ID and to do this search, and then taking the maximum and minimum MJD values of each of the measurements of the set of measurements, and then subtracting it to get the duration. So that's what this cell is doing. So we'll execute that here. It says it takes 4 minutes, but I think it's going to be quicker than that. Because yeah, what this is doing is it's iterating through all of these thousands of DIA objects, and then each of the like the tens of DIA source detections for each of these objects. So this could take a little bit longer, but hopefully it's a little bit quicker than 4 minutes.
Mine was 2 minutes and 37 seconds.
Okay, not bad. Yeah, we'll race. We'll see how long this takes. Oh, does it? Yeah, will it say?
Yes, when it finishes, I think it'll put the duration in.
Okay. Yeah, I'm really not sure what's causing this weird, kind of like weird black bar here.
Ryan, do you know what the tight layout command is just above in the box just above it?
Oh, this?
Yeah.
Yeah, so when I use that, I use it to like make the plots look nicer. And usually it cleans up any kind of open space that's around it. That might be what's doing that. I see a couple of things in the chat here. Yeah, okay, so yeah, Tom Laredo tried taking that out, and that band is still there. And then yeah, Alan Jackson suggested that there's too many ticks in that link that they sent. So that might be the issue. So there's probably some way to address that. What happens if you do this? Oh, I need to wait for this to finish up though. Because it's taking longer than 2 minutes. Yeah, and then I guess I can pause here if there's any questions or comments so far on this.
It's not just too many ticks. It looks like there's too many numbers also.
Yeah, I think, the too many ticks is causing that first black bar, and then the too many numbers on the bottom part.
Correct. Yep.
Yeah. Okay, I'm gonna make a note about this. Okay, yeah, thanks, Alan, for suggesting that. Yeah, I think there's something weird there. We need to restrict the number of ticks that are displayed. Yep, so if there's any other questions or comments so far as we kind of wait for this to finish up. Yeah, maybe it will take 4 minutes to do this. Yeah, I'm hoping there's not something wrong on my end. So is this also taking, is this still running for people?
Yes, I think also maybe we're all submitting things at the same time, so that might be slowing things.
Oh, yeah, that could be it.
I did mine early.
Okay. All right, well, if this takes a little longer, I'll wait like another minute. I already have this executed on another notebook, so I can pop over to that if this is still taking. Okay, Valeria said it's taking more than 8 minutes. That's long. Okay, all right. So what I'm going to do is I'm going to skip to another instance of the notebook where I've, oh, did it just finish? Oh, cool. Okay, it just finished. It took 4 minutes and 48 seconds. So I guess pretty much what it described here, 4 minutes. Okay, so hopefully that finishes up for everyone. Let me continue on here. Yeah, okay, 4 minutes and 50 seconds. Interesting. Yeah, I think that was much quicker when I tried running it earlier. I guess it is probably is that we're all doing it at once. Okay, so now what we're going to do in this cell is, now that we have the duration column, which I think we can see if we re-execute this cell. Yep. So we have the duration column here. That's yeah, MJD. So it's probably in days, I would think. So now we can apply these duration constraints that we had. So the minimum duration and the maximum duration that I believe was like 50 days and then like 300 days. And then it looks like there are 40 of these 1,000 candidates that pass through this duration cut. Now we can plot a histogram of the light curve durations, scatter plots of these things. And okay, we're having the same kind of like too many ticks and too many plot things here. So yeah, we definitely need to check that out to make this a little more legible. But yeah, I think the thing to point out here is this is the duration and the number of supernovae that fall in this range. And there's something, this seems a little strange. There's some outlier here that might be worth investigating. I think that's probably this one here. So basically just coming up with a couple of plots to figure out or to interpret the 40 candidates that we have here. Okay, and then now in section 3.4, we can actually plot the multiband light curves of just 20 of these supernovae, since we don't want to plot everything and to kind of overwhelm the screen with a bunch of light curves. So we'll plot here. This is searching for these different, let's see, we're searching the DIA source table to grab the light curves, or to grab the photometry, again, iterating on the DIA object ID, and then plotting for every filter using a different plot symbol. And yep, that's kind of, so that's, this cell here is just set up to do this search to grab the photometry. And here's another, yeah, this point here to keep in mind, right, that this is not really a complete sample because it's just using the parameters that we've specified. So, right, it is good enough for a demonstration, but if you want to do a more rigorous classification, you probably need to apply better constraints or use different types of maybe techniques for identifying and making sure your sample of supernovae is complete. And so here's the output of the light curves, the first 20 light curves of the 40 supernovae that we have. And so you can see that they look somewhat 1A like. This one looks a little weird. Some of them are a little funny, so maybe some of them aren't real. But yeah, this did a pretty good job at identifying things that look like 1A supernovae, so like that have a rise here and this gradual decline that fit into that duration constraint that we have. So yeah, for a first go, this does a pretty good job at getting these candidates. Okay, so now this is the new stuff here. So what we added is forced photometry light curves. So this kind of the kind of logical flow in going through this notebook here is, all right, now that we've got our sample of interesting 1A supernova candidates, we want to do a more detailed analysis on some of the candidates that we think could be real or could be interesting. So while we can use the DIA object table to search for interesting transients or a specific type of transient that fits our constraints, we can now use the force source on DIA object table to do a more detailed analysis of any of these interesting sources by applying the force source photometry. So now instead of just looking at the DIA object or DIA source table where there's greater than 5 sigma detections, we can look at this force source on DIA object table where you have all forced PSF photometry on every single visit image that includes that object. So that's one thing that you might want to do if you do this kind of exercise. We see an object that looks interesting and you want to know more about it to see if there's any other type of variability or anything interesting that it might have done outside of this detection here of the outburst or explosion. So again, if you want to, you could print out the different columns of that table, or like I mentioned in the schema page, you could just go to force source on DIA object here and kind of read through what each of the columns or these properties that the table provides. So yeah, this set of values here. Oops, this is a different one. Let's see, I'm trying to go back to my other thing, but the Zoom window is blocking it. Hang on, so I'm going to stop screen sharing for a little bit. Okay. Okay, so what we're going to do is we're going to look at a particular DIA object that's we've known is interesting. So we'll retrieve the photometry for this particular one here, this DIA object with this super long string of numbers. This one here. So this one probably is not going to pop up in this set of 20 here, since the ones that are shown are kind of random, where they might change every time you run the search. This is just one that we know is interesting and that we can is a good example to use to try to apply this force source on DIA objects table analysis on. So this is just a query here to extract these different values or these different parameters of that particular DA object. So the way we can search through this force source on DA object table is just with a given DA object ID. So we put that in there, and then we'll get all of these different parameters out. So for example, there's the PSF difference flux, which is the force source photometry on the difference image. And we can also get the force source photometry on the non-difference image that's also provided in this force source on DA object table. And so that's called PSF flux. So there's PSF diff flux and PSF flux. So the diff flux is the force source photometry on difference images, and then the PSF flux is on direct images. So we can get both of those on the force source on DA object table. So let's execute that. And we do a join here with the CCD visit table because I guess right now, at least, the force source on DA object table does not have the time of the observations, but it gives the CCD visit ID, which we can use to do a table join with the CCD visit table that tells you what the time of the observations are. So we're just using that so we have we can make a light curve essentially, so we know what time the observations happen. Okay, and then we'll save the results here in this cell as a forced source, so we can distinguish it from all the other ones that we saved. And then let's see here. Let's see what we're doing here is, oh yeah, so we can also, as a comparison, we're going to use the DIA source table to get the DIA source light curve of this exact same object. So this will be interesting to look at because in the DIA source table, you're only getting the light curve measurements or photometry where your signal to noise is greater than 5. Whereas here in the force source on DIA object table, you're getting all of the images, even if there's nothing there. So this is this cell, so we'll execute that. And then this is just defining a signal to noise value, because although it's provided in the DIA source table, there's no parameter currently for a signal to noise in the force source on DIA object table. So we're just defining that here. And then if you want to, we can show that this column has been added here. So this is our force source on DIA object table. So it has a DIA object ID, it gives the band, the CCD visit ID. And here are the fluxes for each of the force source measurements on each visit and the signal to noise here. So you can see that it's like some of these, you have a very low signal to noise because there's probably nothing really there in that visit image. And you wouldn't get these values or these entries in the DIA source table because it falls below that 5 sigma threshold. Okay, and then in this section 4.2, we can actually plot these light curves. Just defining on when here we're just defining the where the full light curves start and end. So using the minimum and maximum I guess times of the observations from each table, the DIA source table and the force source on DIA object table. And let's plot this here. Okay, so in the gray, these are the this is showing the duration or the duration of the light curve or the times that span the detections provided from the DIA source table. So these are the measurements of this DIA object, so this supernova, where the photometry is above 5 sigma, or the robustness of the measurements is above a 5 sigma detection. And here on the left, this is the force source on DIA object, results from the force source photometry from this table. So you can see that it spans this time scale is much longer than what's provided in the DIA source table. So if you were worried about this candidate, supernova candidate, having some kind of pre-explosion variability that might make you more skeptical of what its classification actually is, this is exactly what you would want to do to see if there's anything funny going on here, or if there's anything that's maybe below 5 sigma that you're looking for, any type of that kind of variability. And that's why you see much more detections here in the force source on DIA object table than the DIA source table, because you're looking below 5 sigma, and you're looking at what the forced PSF photometry measurements are at that position of the DIA object in every single visit. And then let's see here. This is just showing the difference between the force source photometry and then the DIA source here, looking just more closely at that same range where the DIA source detections are made. So you can kind of see here too that there's some detections even within the duration of the DIA source detections. There are some here that pop up in the force source table on DIA object table that aren't here because the signal to noise of these measurements are probably below 5 sigma. Yep, and then so in each of these other cells, it's kind of just going through identifying where the missing measurements are. So the ones like where, like these black Y band points here, maybe these U band points and some of these here, we don't see those in the DIA source light curve. And so you can, this cell just identifies like how many measurements are in one table and how many are in the other. So there's more measurements in the force source on DIA object from the DIA force source on DIA object table than the DIA source table here, which is what you'd expect, because if you're doing, you're sampling all the visits, regardless of what the signal to noise is, it's going to be, you're going to have more measurements there. There's no constraint on the signal to noise. And this here, let's see, this is looking at, unique visit IDs of this. And then still trying to find the missing measurements here. And then if you look at this table of the missing measurements from the DIA source, you can see that the signal to noise is all below 5 here. So these 13 points that are missing from between these 40 and 13 measurements, so these ones here, all have a signal to noise less than 5, which is why they're not in the DIA source table. It's only in the force source table where you have these measurements below this 5 sigma threshold. And then if you want to, this cell here just shows that the maximum signal to noise in this table is indeed below 5 sigma. Okay, so I apologize in advance. I guess I probably didn't time this that well, where I can't really get to notebook 07B, but I hope to get to that in future delegate assembly, because there's some cool stuff there. So what I'll do is I'll just finish off the rest of this notebook, and then after that we can maybe take a break and then go to the do some breakout rooms. All right, so in the final part of this 07A notebook here, one thing that we might want to do is like take a look at this, and then just if we're doing analysis on real data, what we might think as we're looking at this forced photometry light curve is, okay, it looks like there could be some pre-explosion variability that occurred maybe here, like maybe this Z band point is something interesting. Although it doesn't pass a 5 sigma threshold, it's like 3-ish or above 3. So maybe this is real, and maybe this is something we want to look at more closely. And so that's in that section. It shows how we can do that. Let's see here in section 4.4. So yeah, I guess, yeah, an important thing to highlight though is this is just for demonstration purposes. This was not simulated in DP 0.2. There's no pre-explosion outbursts or anything. So it's just some kind of noise that was incorporated in the simulated data. So kind of just an exercise of if we had our real data and we saw this, how can we proceed to do that? So the flare filter that we were looking at looked like it was a Z-band. So we're just defining that here. This is just this command here, the sigma clipped statistics is just to get the median and standard deviation in that flare filter for the PSF fluxes, difference fluxes that we get. And then this is just showing what the median values are and the standard deviation. And so, yeah, I guess it's negative because maybe the reference image was a bit higher, or the reference image flux might have been taken a bit higher. So you can see, it looks possibly like you might get a negative flux for the median. Okay, let's see. So here, we're just looking at, let's see, define where any outlier variability might be. So yeah, we're looking at points above 3 sigma. Or identify, yeah, trying to find where points are above 3 sigma. And there's one point identified here, looking at our Z-band filter measurements. And it's this one here, but this is strange because it's showing a difference signal to noise of 2, which is not right. So let me double check this. Okay, I'm going to make a note here because this does not seem right. It should be above signal to noise of 3. So my guess is that there's some, that the index here is not, it's not quite right. Okay, well, let's see. I'm going to look into this to see why it's not identifying the right measurement here. Or maybe I'm doing something weird if someone has caught an error that I made. But basically, we're going to look at that point here, and it should be above a 3 sigma measurement. So I'll double check that.
But the median was negative, no? Was it?
Yeah, I think it should just. Yeah, the median was negative for all Z4 sources. Median plus 3 sigma. So this should be. Yeah, so it should be looking for things with difference PSF flux measurements greater than 1,661 nanojanskis. And so that looks like that's correct here. The PSF diff flux is greater than the median plus 3 sigma. Unless the difference signals to noise is calculated incorrectly. No, it's not. Oh, okay, I see. So I think what the issue here is it's the signal to noise that we're defining here is based on the distribution of the signal to noise that we're defining here is based on the scatter of the Z-band measurements. And so that's how we're defining the, I guess the standard deviation of the Z-band measurements, and that this is 3 sigma above those of those there. So for example, so the standard deviation is 568, and the measurement here of the PSF diff flux is 2,517. So that's like a 4.4 sigma. But this is coming from the PSF diff flux here and the PSF diff flux error from the forced PSF photometry measurements. So the forced PSF photometry measurement is below 3 sigma, but if we're looking at the distribution of flux measurements, then that appears to be above 4.4 sigma. And that's confusing. So I think we should probably clear that up in this notebook section. Yeah, sorry about that. It's a little confusing. Okay, but basically the point here is just to show where that measurement is, and that could be this potential flaring activity. And this is the standard deviation of the Z-band force source measurements here, to show that you have something above 3 sigma of the measurements. So that might be something we'll need to edit this or update this notebook a little bit to make that a little more clear there. All right, so yeah, I apologize that took a little bit over, and there's some bits that we need to clarify a little bit, but I hope this was useful for getting an idea of the differences between the DIA object catalog and the force source on DIA object catalog, and how you can apply those to your own science cases. And that this really does provide a nice example of how you can really start utilizing these different catalogs to do your own science, not just on like 1A supernovae, but if you have a type of transient that you're interested in investigating, where you know the amplitude or duration, you can just modify this to you can modify this notebook to suit your own needs for your own searches. Okay, so let me stop.
That was
sharing.
really good.
Yeah, thanks.
That
Yeah,
was awesome.
yeah,
And the fact that you went relatively slowly through this was very helpful. You know, I could follow it quite well. So thank you, Ryan. Great.
yeah. Thank you for the positive feedback. Yeah, I apologize I couldn't quite get to 07B, but perhaps in the next delegate assembly I can go through that, because we did similar updates there, and that one's focused more on variables for RLI arrays. And then also doing the force source and data objects. Yep.
I think we have some open assemblies that would fit in there nicely. So very good.
Okay, sounds good. Yep, and then let's see, I guess we can do breakout rooms if people want to do that. Are there any suggestions for different breakout rooms?